Okay. So, good morning, students. Is it audible? Voice is audible? Can you hear my voice?
Yes,
The,
sir.
okay, thank you. Whether you see the slide? Okay. So, I will start the lecture. Mm, Actually, the basics for lattices is has diagram. There is a partial ordering and then has a diagram. So, first I will tell uh, explain partial ordering and then has a diagram and then I'll go to lattices. Okay. So partial ordering means a relation or on S is called partial ordering or partial order if it is reflexive, antisymmetric, and transitive. A set S together with a partial order is called ordered set or just poset. For example, uh, here the set is a set of all integers and the relation is greater than or equal to. So we are going to check uh, the set of all integers with respect to the relation greater than or equal to is partial ordering. So we know that in integers a is greater than or equal to a for every integer. So that's why greater than or equal to is what reflexive. And for antisymmetric, whenever a greater than or equal to b and b greater than or equal to a, so should assume these two. So a equal to b. So and hence the relation is greater than or equal to is what antisymmetric. Third one transitive. A greater than or equal to b and b greater than or equal to c implies a greater than or equal to c. This is automatically comes. So that's why greater than or equal to is transitive. We proved it is reflexive, antisymmetric, and transitive, and hence this is what partial ordering on the set of integers, or you can say in short form poset. Partially ordered set means PO set. Okay. So second problem, show that the divisibility relation. This is actually backslash. Divisibility is a partial ordering on the set of positive integers. So here the set is z plus. Z plus is set of positive integers, and the relation is divides. So we know that a divides a for any positive integer. If you take any elements from z plus, that elements divides the again that the same element. So that's why a divides a for any positive integers. This is true for every a in z plus. So that's why this divides is reflexive. Next, you should assume uh, a divides b and b divides a. That is a related to b and b related to a. So then a equal to b because a divides b and b divides a implies what a equal to b. So this implies L is antisymmetric. Not sorry, it's not L. Actually, this is what divides. Next, you should assume A related to B and B related to C. So this A divides B and B divides C. Automatically, A divides what? C. Okay, then the relation divides is transitive. So we proved reflexive, antisymmetric, and transitive, and hence the relation divides is a partial ordering on Z plus. Third example, set inclusion. So set inclusion, this is a notation. Okay. So what is a set? Set is power set of S. S is a given set. Power set of S is the uh, uh, your set. You know what you mean by power set of S, which contains all the subset of S. Okay. So first, uh, A, A is a subset of A. Okay. Whenever this A is a subset of S. Okay. So from S, I am taking a subset A. Okay. So that subset is a subset of itself. If you take any subset from S, this this is true. So and hence the set inclusion is what? Reflexive. Next, I will take two sets. Okay, for three sets we need for transitive. For two sets we need for antisymmetric. So okay, A is a subset of B and B is a subset of A. Then A equal to B. That is A related to B and B related to A implies what? A equal to B. So and hence the set inclusion is antisymmetric. So to prove transitive, we need three sets. So three A, B, C are any three subsets of S. A is a subset of B and B is a subset of C. That is A related to B and B related to C implies A related to C. A is a subset of C. And hence the set inclusion is transitive. And hence the relation set inclusion is a partial ordering on the power set. P of S means power set of S. Okay, so these examples are very similar to what we discussed. That's why just I will tell and then quickly I will go to the next slide. So provide an example of partial ordering on R. R is what? Set of all real numbers. Actually, they are asking the relation. Okay, so either the relation is either you can take less than or equal to, or you can take what? Greater than or equal to. R with less than or equal to is a partial ordering. Similarly, R with greater than or equal to is a partial ordering. So next, again set inclusion. Here they gave some particular set A equal to ABC. For this set, you need to find a power set. So it contains three elements, means 2 power 3, it contains 8 elements. Okay. So actually 3.50 example is a particular case of 3.48. So that's why I'll skip. Okay, you can try. Similarly, describe whether the relation divide and multiple integral are partially ordering. So already in example 3.47, we discuss divisibility is what? On set of positive integer is a partial ordering. Similarly, okay. So similarly here, okay, as in the as I told us, the relation divisibility is a partial ordering on a set of positive integers. So here what? The same idea. Okay, you should use the describe whether the relation divide and multiple integral multiple or partial ordering. So how we proved divide is a partial ordering. Similarly, you can prove what? Integral multiple is also what? Partial ordering. So A divides A here, divides here what? A is integral multiple of A. So for reflexive. Here what we done? A divides B and B divides A equal to A equal to B. Here integral multiples la A is B is an integral multiple or A is integral multiple of B and B is integral multiple of A implies what? A equal to B. Here A divides B and B divides C implies what? A divides C. Here in integral multiple, uh, B is an integral multiple of A. Next what? C is a integral multiple of A implies what? Sorry. You should assume B is integral multiple of A and C is integral multiple of B, implies C is a integral multiple of A. Okay, so more or less the same idea. Okay, next has a diagram for partial ordering. Okay, so here since partial ordering is we know that it is reflexive, its diagram has loops at all vertices. So there are three roots here. Okay, since it is a the partial ordering is a reflexive relation, we need not to show these loops, okay, self loops, since they must be present. Since the second one, the partial ordering is a transitive. We need not show those edges that must present due to transitivity. For example, if 1, 2 and 2, 3 are edges in a diagram of a partial ordering, 1, 3 will also be an edge due to transitive. So the edge 1, 3 need not shown in corresponding hash diagram. Next, third rule: if you assume that all edges are directed upward, we need not show the direction of the edges. Okay, so that's the hash diagram representing a partial ordering can be obtained from its diagram by removing first all the loops, by removing all edges that are present due to transitivity, and by drawing each edge without arrow so that its initial vertex is below its terminal vertex. Okay, so here for example, let us construct the Hasse diagram for partial ordering. Set of all the order pairs A comma B such that A less than or equal to B on the set 1 comma 2 comma 3 comma 4, starting from its starting from its diagram. Okay, so here A comma B, A less than or equal to B. So 1, 2, 3, 4 you should write. So 1 is less than or equal to 1, so that's why self loop. Okay, similarly for each you have self loop. 1 less than or equal to 2, so there is a direction from 1 to 2. Similarly 2 to 3, 3 to 4, and then 1 to 3, 1 to 4, 2 to 3, 2 to 4. So okay, first this is the initial diagram. Okay, from here to here, okay, due to a reflexive, you can remove the self loop. Okay, first, because it is reflexive, we know that's why we remove the self loop. From here to here, we remove the edges due to transitivity. From 1 to 2 you have the edge, from 2 to 3 you have the edge, so naturally 1 to 3 is also there is an edge, so I removed 1 to 3. Similarly, I remove all the edges due to you have for transitivity relation from here to here. Next, from here to here, I remove the upward arrows. Okay, so this is the final diagram. Actually, in the classroom, I told the students. I think the answer who gave the answer for that question is also attending this lecture. So okay, I think okay, just for remembering the ideas, I told, and I think I will tell in Tamil. Okay, I actually Parthiban vadival comedy. I think okay. So இங்கு நல்ல மீன்கள் விற்கப்படும். So this diagram from here to here, so remove இங்கு, here நல்ல மீன்கள் விற்கப்படும், here மீன்கள் விற்கப்படும், here விற்கப்படும். Actually, I gave this idea only, and then I told there is a similar type of comedy is in Tamil movie. At present, one student from AADS exactly found out Okay, so okay, now I'll go to the next. Okay, hash diagram. Okay, so next problem is draw the hash diagram representing the partial ordering set of all a comma b such that a divides b on 1 comma 2 comma 3 comma 4 comma 6 comma 8 comma 12. Okay, so a the set of all a comma b ordered pair such that a divides b. So here you need to draw the hazard diagram. Okay, see what is 1 2 3 4 6 8 12. Okay, so 1 divides what? 2, 1 divides 3. Similarly, 2 divides what? 6, 2 divides 3 divides 6, 2 divides 4, and then 4 divides 12, 4 divides what? 8. So this is the hazard diagram. Okay, so you need to draw and you need to practice. Okay, if you see the lecture, you can easily understand, but practice is more important. You'll try some other problem. Okay, next draw the hazard diagram for the following situation. So here the set is 1 2 3 4 and the less than or equal to be the relation. Okay, so 1 less than or equal to 2, so 2 less than or equal to 3, 3 less than or equal to 4. Okay, so this is the hazard diagram. Next draw a hazard diagram for the partial ordering set of all a comma b such that a is a subset of b on the power set p of s, where s is equal to a comma b comma c. Okay, so here s is equal to a comma b comma c, and the power set, you know that which is a subset of uh, S. So empty set, singleton set A, singleton set B, singleton set C, and then AB, AC, BC, ABC. So these are all the power set of what? S. Now the hazard diagram you need to draw here. Okay, so next slide. Okay, so this is the empty set. Empty set is a subset of what? Singleton set A. Empty set is a subset of what? Singleton set B. So empty set is a subset of singleton set C. Okay, next singleton set A is what? Subset of AC, and then C is what? Subset of what? AC, and then C is a subset of BC, and B is a subset of BC. Okay, and then A is a subset of AB, B is a subset of AB. Next, AC, this set is a subset of ABC, AB is a subset of ABC, BC is a subset of ABC. So if you have any doubts, you can ask. Okay. Okay. Next, the set X 2, 3, 6, 12, 24, 36, and a relation less than or equal to. Okay. Here, less than or equal to means not usual less than or equal to. So you should be careful. So less than X less than or equal to Y means here what they give, X divides Y. Okay. So draw the hazard diagram of X less than or equal to. Okay. So here 2, 3, 6, 12, 24, 36. So, okay, 2 divides, here already told, less than or equal to means what? Here if x divides y. So, 2 divides 6, 3 divides 6. 6 divides 12, okay, but 12 divides what? 24 and 36. This is the hazard diagram for this set together with this relation. Okay. Okay, let A be a finite set and something rho or P of A, okay, or rho of A be its power set. Let this is the set inclusion relation on elements of power set of A. So draw the hazard diagram, okay, of P of A or row of A, comma set inclusion for, okay, here actually this is A equal to, here equal to is missing, okay. So A equal to the set A, and B equal to A comma B. Here B equal to, it is clear. So now, so A equal to singleton set A. What is the power set of A? Empty set and the singleton set A. Only two elements. So diagram is empty set. Here singleton set A. So empty set is a subset of what? Singleton set A. That's why this should be uh, below two singleton set A. Okay. Next, A equal to what? A comma B. It contains, power set contains four elements: empty set, singleton set A, singleton set B, and then AB. The diagram is, you can see here. Okay, it is not, I think, clearly. Okay, assume this is empty set. Okay, okay, assume this is empty set. Sorry, this is empty set. This is what? Singleton set A, and from here to here, singleton set B, and then from A to A comma B, from B to A comma B. That's all. Okay. Okay. Next, we are going to define four definition. Okay. First one is maximal member, and then minimal member, and then greatest member, and then least member. Okay. So, okay, before going to the definition, I will show you the example. First, we will discuss the example, and you can tell anyone of them tell the answer. Okay, because if you tell the answer, then only I know that whether you somewhat understand. Okay, maximal member, minimal member, greatest member, least member. Okay, you should remember first these four keywords. Okay, so here, what is A? So in this diagram A, D, A is what? Least element, and also it is a minimal element. Okay, A is a least element, and also A is what? Minimal element. Here D is what? In this example, D is the greatest element, and also it is a maximal element. Okay, so now come to this diagram. See, A is what? A is the least element, and also it is a minimal element. What about C and D? C and D are maximal element. Here, greatest element is not exist. So, okay, greatest element, because you cannot compare C and D. So this is also maximal. This is also maximal, but you cannot compare C and D. Okay, so that's why here D is the greatest element. Okay, because D is bigger than the remaining thing. So that's why here C and D are maximal by definition, but here greatest element is not exist. Similarly, here D is the greatest element, and also D is maximal. Here A and B are minimal element, but here least element is not exist. So in the first diagram, A and B are minimal element. Here least element is not exist. Here D and E are maximal element. Here greatest element is not exist. Okay, now I'll go to the proper definition. Okay, so when P comma less than or equal to is a poset or partially ordered set, an element A in P is called maximal member of P if there is no element, okay, there is no element B in P such that A less than B. So you cannot find a B such that. So then only it is what? A is a maximal member. Similarly, minimal member definition, an element A in P is called minimal member of P you cannot find an element. Okay, if there is no element b, means that you can also say there is, you cannot find an element b such that b less than or equal to what, a. Okay, so next, if there exists an element a in p such that b less than or equal to a for all b in capital P. Okay, wow. So then only you can say this a is what, greatest member. So okay, so a I am comparing with all elements of what, capital P. Still it is bigger, so that's why it is the greatest member. Similarly, if there is an element a in P, that a is less than or equal to for all the elements b in capital P, then that's why a is called least member of the poset. Okay, so now the maximal, minimal, the greatest and least member of a poset can be easily identified using the Hazer diagram of the poset. They are the top and bottom elements in the diagram. A poset can have more than one maximal member. Okay, here you can see more than one maximal member. Similarly, more than one minimal member. Okay, uh, yeah, a poset can have more than one maximal member and more than one minimal number, whereas greatest and least members, when they exist, are unique. So this is the greatest element, it is unique. This is the least element, so here it is exists, it is unique. Okay, I think the remaining thing is about this diagram 2.16a. Okay, so already we discussed this one. So next definition, upper bound and then least upper bound, and then lower bound, greatest lower bound. Okay, so only these two definitions, and then we will go to the problem. So I think slightly, okay, I will explain, try to understand. Okay, a is a subset of the poset. Okay, p comma less than or equal to, poset means partially ordered set. And if small u is an element of capital P such that a less than or equal to u, okay, for all elements a in capital A. So a is a subset of P, u is an element of capital P such that, okay, this u is, okay, bigger than all the elements, okay, small a, where small a lies in what, in this subset. Then you say this u is called an upper bound for this subset A. Similarly, if L is an element of P, so already you took u is an element of P, now L is an element of P, just opposite condition here. L less than or equal to what, A, for all elements A in capital A. So then we say that this L is called what, lower bound for this subset A. Okay, so here we defined what is upper bound of a subset of a poset. Similarly, we defined lower bound of a subset of a poset. Okay, next, the upper and lower bound of a subset of poset are not necessarily unique. So first you should know, upper and lower bound of a subset of a poset are not necessarily unique. Okay, so next, the element x is called least upper bound or LUB or supremum. All of them are same. Okay, of the subset A of the poset p comma less than or equal to, if x is upper bound, x is an upper bound, okay, that is less than or equal to every other upper bound of A. So among the upper bound, we need to choose the least one. So that is called least upper bound. Similarly, the element Y is called greatest lower bound or GLB or infimum of the subset A of the poset P comma less than or equal to if that Y is a lower bound that is greater than every other lower bound of A. So among the lower bound, which one is the biggest or which one is the greatest is called greatest lower bound or infimum. Okay. Note the lower bound, the LUB and GLB of a subset of the poset, if they exist, that should be unique. For example, let us consider the poset with the Hasse diagram given in this figure 2.17. The upper bounds of the subset A, B, C. Okay, the upper bounds of the subset here instead of capital A, we have what? Capital A is what here? ABC. What is the upper bound of ABC? E and F. Here D is not an upper bound. The reason is C is not related to what? D. Okay. So now the upper bound of ABC is what? E and F. Okay. Now among E and F, which one is the least? E. That's why the least upper bound of ABC is what? E. Okay. Next, lower bound of the subset DE. Okay. DE, what is the lower bound? Okay. A and B are lower bound for the set D and E. But C is not a lower bound because C is related to E, but C is not related to what? D. So that's why the lower bound for the set D and E are A and B. Among A and B, which is the biggest one? So B. So the greatest lower bound of the set D and E is what? B. So the greatest lower bound of D and E is what? B. Yes. Okay. Next, which element of the poset? Here it is not clear. I will read. Okay. The set 2, 4, 5, 10, 12, 20, 25, division slash or maximal. Okay. Which elements of the posets are maximal and which are minimal? So again, you need to draw the Hasse diagram first. So here 2 divides 4 and then 2 divides what? 10. Okay, 5 divides 10, 5 divides 25. Okay, and then you should draw very carefully. Okay, and then 4 divides 12, 4 divides 20, 10 divides 20. Okay, now what is the maximal element here? Already I told you. Here maximal elements are 12, 20, 25. These are maximal elements 12, 20, 25. The minimal elements are 2 and 5. Minimal elements are 2 and 5. You can see in the next slide. The maximal elements are 12, 20, 25. 12, 20, 25. The minimal elements are 2 and 5 as we discussed in this diagram. So this is maximal elements, minimal elements. Okay. Next, find the greatest lower bound and the least upper bound of the set BDG if they exist in the poset shown in figure. So BDG. Okay. So for BDG, okay, what is the upper bound for BDG? Okay, so naturally you should tell what? H. But here, okay, G is also upper bound. Okay, because by definition, upper bound definition, okay, so yes, a relevant u of a relevant u of p such that a less than or equal to u. Okay, I don't tell strictly less than here. So a is a subset of a poset p comma less than or equal to, and if u is an element of p such that a less than or equal to u for all a belongs to capital A. Okay, so you should remember this definition. So I'll come here. Okay, okay. So actually here the set is capital A is what? B D G. Okay, I think yeah, B D G. Here by the definition, okay, so B less than or equal to okay H. Okay, D less than or equal to what? H, and G less than or equal to H. Similarly, B less than or equal to G, D less than or equal to what? G. This is D. Next, G less than or equal to what? G. So, and hence H as well as what? G are satisfying this condition. So that means these two are upper bounds. Among these, which one is the least? Okay. So G is the least. So G is the least upper bound. Similarly, okay, B, D, G. Lower bound are A and B. The same idea again. So the greatest one is B. Okay. So B is the answer. Next, I will go to next slide. Okay. So you can see here the the upper bound for BDG is what? G and H. Since G less than H, G is the least upper bound. The lower bound of BDG are A and B. Since A less than B, B is what? Greatest lower bound. And next problem. Find the greatest lower bound and least upper bound of the sets 3, 9, 12 and 1, 2, 4, 5, 10. If they exist in the post set Z plus means set of all positive integers. The relation is a division. Okay, divides. So we need to find first lower bound and then greatest lower bound. First I will fix 3, 9, 12. So here the relation is less than or equal to. So the lower bound of 3, 9, 12 with respect to division means, so we need to find a number which divides these three numbers. Okay, so 1 and 3 divides these 3, 9, 12. So among 1 and 3, which one is the greatest? So 3 is the greatest. Okay, so 3 is the greatest lower bound of this set. Similarly, again this set I'll take 3, 9, 12. You need to find the upper bound first. So that means upper bound and the least upper bound. The least upper bound is nothing but LCM. Because here in this example, the greatest lower bound is what? GCD. GCD. Because the binary, sorry, the relation is what? Less than or equal to. What is the GCD for 3, 9, 12? 3. Similarly, what is the LCM for 3, 9, 12? 3, 9, 12 LCM is 36. So 36 is the least upper bound. Similarly, for 1, 2, 4, 5, 10. So for this, you need to find the lower bound. Lower bound is 1 because 1 only divides everything. Okay, so the lower bound is 1. So, and hence the greatest lower bound is also what? 1. Okay, for this set, you need to find the least upper bound. The least upper bound means you need to find the LCM. So, LCM is LCM of 1, 2, 4, 5, 10 is 20. So, 20 is the least upper bound. Okay, you can check it. If you have a doubt, you can ask to me. Okay, so now we are going to slowly introduce the lattices. So, okay, I think you know what you mean by equivalence relation. There is a equivalence relation means what? The relation R is a reflexive, symmetric, transitive, and relation R is a partial ordering means it is a reflexive, antisymmetric, transitive. And then we saw this type of hazard diagram already. So instead of 1, 2, 3, we discussed what? ABC. Here, the power set of 1, 2, 3 and set inclusion. So empty set, and then here 1, here 2. Okay, you can easily write, just replace ABC by 1, 2, 3 and then draw the diagram. Okay. So next, here n equal to 12. So d of 12 means divisors of 12. So n equal to 12 and x is the set of all positive integers which are divisors of 12. So you know what is the divisors of 12? 1, 2, 3, 4, 6, 12. And here the less than or equal to be the relation is divisor of. Okay. So 1 divides 2, 1 divides 3, 2 divides 6, 3 divides 6, 2 divides 4, 4 divides 12, 6 divides 12. So this is the hazard diagram. Next, x is equal to 1, 2, 3, 4, 6, 12. The same, actually, this is also a divisors of 12. The same set. Okay, wow. But here the relation is divisor of. Here the relation is less than or equal to be the usual less than or equal to relation. So a less than or equal to b if and only if b minus a is non-negative. So that means 1 less than or equal to 2, 2 less than or equal to 3, 3 less than or equal to 4, 4 less than or equal to 6, 6 less than or equal to 12. So this is the hazard diagram. Okay. Next, definition of chain, okay, or a totally ordered set. A partial order relation less than or equal to on a set capital A is called a total order or linear order. Okay, if for every a comma b in capital A, either a less than or equal to b or b less than or equal to a. Okay, so if less than or equal to is a total order on A, then the post set a comma less than or equal to is called a chain or totally ordered set. So I told in the class actually what do you mean by chain? Chain means if any two elements is comparable. Okay, either you can say a less than or equal to b or what? B less than or equal to a. So then only we say that set A is a chain. So simply, if you want to say a set A is a chain, if any two elements are comparable. Okay. The poset given in the example 5. Example 5 is a chain. Actually, this is also a chain because you can compare any two elements. Okay. Example 5. Yeah. Example 5. This is a chain. But the power set of P of actually this is also not a chain. Okay, because 3 is not related to what? You cannot compare 3 and 4. That's why this is not a chain. Similarly, 3, okay, the set 3 and set 1 comma 2, you cannot compare these two. Okay, So that's why it is not a, this is also not a chain. Okay, so already we discussed upper bound, least upper bound, and lower bound, greatest lower bound. Here there is something another slightly another version, but more or less same. Let x comma less than or equal to be a poset, and a comma b in capital X if there is an element c in capital X such that a less than or equal to c and b less than or equal to c, then C is said to be upper bound for A and B. C is upper bound for A and B. An element C is of in X is said to be a least upper bound of A and B if first that element C is an upper bound of A and B, and whenever D is an upper bound of A and B, okay, then the C should be less than or equal to what? D. That means if you want to say C is an upper bound of A, C is an upper bound, an element is C is the least upper bound of A and B. Now, first C is an upper bound of A and B, and whenever among the upper bound of A and B, C should be least. So that is the second condition. Next, an element C is said to be lower bound of A and B, then if C less than or equal to A and C less than or equal to B, okay, an element C is said to be greatest lower bound of A and B if C should be lower bound of A and B. Okay, so among the lower bound of A and B, okay, suppose D is a lower bound of A and B, A and B. So C should be greater than what? D. So among the lower bound of A and B, C should be greatest one. So then only we say C is what? Greatest lower bound of A and B. Okay. Next, notations. This is actually let A and B be elements in a poset P x comma less than or equal to the least upper bound of A and B. If, suppose if it is exist, it is denoted by A join B. Okay, if greatest lower bound of A and B exist, then it is denoted by A meet B. Okay, here in this example, X is a set, then they are considering the poset. Poset is P of capital X, that is a power set of X, and less than or equal to is a relation. If A and B are in the power set, okay, the least up A union B, okay, okay, or you can say, yeah, A join B, okay, A join B. A join B means what? Least upper bound of A and B is nothing but what? A union B. Similarly, the greatest lower bound of A and B is what? A intersection B. Okay, next example, in the poset, divisors of 12, comma less than or equal to is a relation is a divisor of. Okay, I'll go to that example. The least upper bound of 2 and 3. The least upper bound of 2 and 3. What is the upper bound of 2 and 3? 6, 12. Among 6 and 12, which is the least? 6. Okay, so that's why the least upper bound of 2 and 3 is 6. Similarly, I'll tell you one more remaining thing, you can check it. 3 and 6, what is the least upper bound? 3 and 6. 3 and 6 upper bound are 6 and 12. So among 6 and 12, 6 is the least. Next, one more thing. 2 and 3, what is the greater? This symbol means meet. So meet means here greatest lower bound. So the greatest lower bound of 2 and 3. Greatest lower bound of 2 and 3. First lower bound of 2 and 3 is what? 1. So greatest lower bound is 1. And For 4 and 6, okay, for 4 and 6, what is the greatest lower bound? 4 and 6, the lower bound is 1 and 2, okay. For 4 and 6, the lower bound is what? 1 and 2. Greatest one is what? 2. So greatest one is 2. Similarly, next, the same set, okay, 1, 2, 3, 4, 6, 12. That is a divisor of 12. But here, the relation is what? Less than or equal to. For 2 or 3, what is the, which example? Actually, this example. 2 or 3, what is the least upper bound? The upper bound for 2 and 3 is 3, 4, 6, 12. So the least one is 3. So similarly, you can check the remaining. Okay. So remark, if A and B are elements in a poset x comma less than or equal to, it is not necessary that the least upper bound of A and B or the greatest lower bound of A and B exist. So, may exist or may not exist. So the following example illustrate this one. Okay. So you can check here for A. Okay. Here the least upper bound of A and B. The least upper bound of A and B is C exist. But the greatest lower bound of A and B is not exist. Even lower bound of A and B is not exist. That's why the greatest lower bound of A and B is what? Not exist. Similarly, next D and F. Okay, D and the greatest lower bound of D and F is what? C. But the least upper bound of D and F is not exist. Okay, the least upper bound of D and F is not exist. Okay, in this diagram, A or B, that means the least upper bound of A and B does not exist. The least upper bound of A and B does not exist. Yes, actually, upper bound of A and B is what? C, D, E. C, D, E. But among C, D, E, you cannot tell which one least because there is no comparison between what? C and D. So that's why the least upper bound of A and B does not exist. Similarly, the least upper bound of A and B does not exist. Yeah, it is given. Note, A and B have C, D, and also E is also a upper bound. Okay, but there is no comparison between C and D. So that's why the least upper bound of A and B does not exist. Okay. Next, definition of lattice. A partial ordered set or poset x comma less than or equal to is said to be a lattice if for every a comma b in capital X, both the least upper bound of A and B. Okay, this notation means A join B means what? The least upper bound of A and B and the greatest lower bound of A and B exist. Okay. Now look at this diagram. Okay, you can check in your free time. Each of the following posets represented by the hazard diagram given in the figure 5 is lattice. Each one. That means if you take any two elements A and B, okay, the least upper bound and of AB or AC or AD exist. Similarly, the greatest lower bound of AB, AC, AD exist or BC. All the combination you can take. Okay, for A and C, what is the least upper bound? Upper bound is what? C and D. So the least upper bound is C. Similarly, you can check. Similarly, A and D, what is the least upper bound? D. For A and D, what is the greatest lower bound? A. Okay. Next, if X is a set, then the partial order, the poset P of X comma set inclusion is a lattice. So already, okay, uh, uh, we saw that, okay, actually where we saw that power set of x is a lattice. Okay, okay. I think we saw that the hazard diagram. Okay, I'll show you. Yes, this one. Okay, but I told this is not a chain. Okay, this is not a chain, but this is a lattice. Why it is a lattice means if you take any two elements, that if you take 1 and 2 3, okay, for 1 and 2 3, what is the greatest lower bound for 1 and 2 3? Actually empty set, s- greatest lower bound. Similarly for 1 and 2 3, what is the least upper bound? X. Okay, X. Similarly for 1 and 1 2, what is the least upper bound? 1 2. For 1 and 1 2, what is the greatest lower bound? 1. So this example is a lattice, but this is not a chain. Okay. So next, so most important note: all partial ordered set are not lattices. Okay. Okay. Determine whether the following posets are lattices. Okay. Here, here set is what, 1, 2, 3, 4, 5, and division. So you need to draw the diagram. 1 to 2, 1 divides 2, 1 divides 3, 1 divides 5, 2 divides 4. Okay. So here there is no, okay, if you want to show that it is a lattices means, so least upper bound of, for any two elements, okay, if you take any two elements, the least upper bound should exist. Similarly, what? Greatest lower bound is exist. Okay. For 2 and 3, okay, well, there is no upper bound for 2 and 3, and hence there is no least upper bound. Similarly, for 3 and 5, there is no upper bound for 3 and 5, and hence there is no least upper bound. So this implies this set together with division is not a lattice, but this is a partial order set. Okay, so this is a partial order set, but this is not what lattices. Sometimes in 2 more question, given uh, given example of a partial order set which is not lattices. Okay, this is an example. Similarly, next one, 1 2 4 8 16, comma division. So here 1 2 4 8 16. So 1 divides 2, 2 divides 4, 4 divides 8, 8 divides 16. Actually, this is like we know that this is chain. Okay, chain is always lattices. Okay, because you can easily find what uh, least upper bound and greatest lower bound exist. For 1 2, what is the least upper bound? 2. Similarly, for 1 2, greatest lower bound 1. Similarly, you can check for all the pairs. So here they are checking the 4 and 6. For example, okay, I think you can easily check 4 and 16. What is the least upper bound? 16. Similarly, the greatest lower bound of 4 and 16, what? 4. So I think they are checking all the pairs. So every pair of elements of the poset has what? Least upper bound and greatest lower bound. Hence, the this partial order set is a lattice. Okay. Next example. Okay. Next, actually, I'll stop up to this. Okay. From here onwards, theorem starts. I will take the theorem in the next lecture. Is the poset Z plus comma division is a lattice. So that means you need to check for okay, for any two elements, the GLB and LUB exist. Okay, if A and B are any two positive integers, what is the least upper bound of these two integers? Is nothing but LCM. That is a least common multiple of A and B, because here the relation is what? Divisor. Similarly, the greatest lower bound of A and B is GCD of two integers. So that's all. The first two and a half line is the answer for this question. Okay, if you take any two elements from Z plus, that's why it is that A and B are two positive integers. Okay, the least upper bound of A and B is nothing but what? LCM of A and B, that is exist. Similarly, the greatest lower bound of A and B is what? GCD of A and B, that is also exist. So here they are just explaining further. For example, consider the set 246. An integer is a lower bound of 246 means if 246 are divisible by this integer. So the only such integers are what? 1 and 2. 1 and 2 divides 246. Among 1 and 2, the greatest one is 2. So 2 is what? Greatest lower bound of 246. Similarly, what is the upper bound of 246? So an integer is upper bound of 246. Now that integer should be divisible by 246. So least upper bound means you need to find the LCM of 246. LCM of 246 is 12. So 12 is the least upper bound of 246. That is also exist. So hence in Z plus, every pair of elements has a least upper bound and what? Greatest lower bound. And hence, therefore, Z plus comma division is a lattice. So to prove it's a lattice, again I'll go to the definition. Okay, a partially ordered set x comma less than or equal to set to be lattices if for every a comma b in x, underline the word, for every a comma b in x, the least upper bound of a and b and the greatest lower bound of a and b exist. Okay, so if you have any doubts, you can ask to me. Otherwise, you can leave. Maybe I will take the next lecture today evening. Maybe. Okay, I will post in the WhatsApp group. Okay, thank you.